title is what can be calculated from a chemical equation. In working with chemical equations and their reactions, the operative phrase will be from me. I don't care what you've done in the past, but this is the best approach to working with chemical equations and stoichiometry of it. Convert to moles, solve the problem in terms of moles. And if the problem is asking you for something else later on, you convert to whatever they're asking for. In the handout, we're using the butane combustion reaction here, and it's going to be 2C4H10 as a gas plus 13O2 goes to 8CO2 and 10H2O. And we'll finish. Let's look. I'm assuming that you understand how to balance an equation, fundamental. The law of mass balance says that by law of conservation of matter, both reactive side equals the product side. But from that, what intuitive quantitative information can you derive from that equation? Basically, from a chemical equation, you can calculate moles, equation mass, particle numbers, gas volumes, and energy numbers, or energy values is more appropriate. Now what I want to do is take that equation and show you how this expands into the various things you can calculate. First thing is moles. Always convert to moles, because the coefficients in the equation are essentially moles. When you look at a chemical equation, it typically is presented in what we call standard form. A standard form of the equation is one in which the coefficients, listen to this, are in the smallest whole number ratio, as shown here. You can't divide them any further. Now you can use fractions as coefficients, but smallest whole number ratios are moles, and that is referred to as the standard equation. And the conditions of the standard equation are 0 degrees Celsius and 1 atmosphere. So you're not going to be given a notation on the side anywhere stating that this is at standard form. When one is written as given in the smallest whole number ratio coefficients, it is assumed to be a standard form at 0 degrees and 1 atmosphere. That is an international standard for chemical equations, molecular equations. The coefficient in this case says we have 2 moles of butane, 13 moles oxygen gas, 8 moles of CO2 gas, and 10 moles of water, liquid. Now, this equation is defined and functions by what we call a reaction ratios. And that seems to be the most difficult hill for students to climb, is to understand what I mean by the terminology of reaction ratios. So I do it like this. If this is the smallest whole number ratio and I double everything, what happens to all the other stuff? If I double butane moles, how many moles of oxygen do I now have to use?
26.
Twice as much. So now with 26, how much CO2 is generated? Twice. Now that's 16, right? And water would be 20. Or I can cut butane in half. What happens to the oxygen moles? Yeah, it's cut in half also. Yes, sir.
How would you cut it in half if it's 30?
You can also get equation mass. Equation mass is moles times formula weight. So if I have 2 moles times the formula weight of C4H10 is on the handout is 58 grams per mole. So that works out to 116 grams. That's the same thing as 2 moles, isn't it? That's just from the standard equation. That's just looking at it. 2 times formula weight. When you look at this, that coefficient is 2 formula weights. This is 13 formula weights. 13 times 32 grams. This one is 8 times the formula weight of CO2. 16, 16, 32, 42, 3, 44. So this is 8 times 44 grams. Am I confusing anybody here? And this one is 10 moles, 18 grams per mole, and it works out to that many grams. This is 416 grams, 352 grams, and 180 grams. Now, if you work the problem first in moles and get the mole value, then all you have to do is multiply by formula weight to get whatever the problem's asking you for in grams. But work the problem in moles first. Always. Convert whatever data you have to moles. So if you're given a quantity of grams, you divide by formula, you get it in moles, and use this standard equation as a ratio. Standard equation is always a given, whether it is or isn't. Particle numbers. Now this is moles times Avogadro's number, really. Avogadro's number is 6.02 times 10 to the 23rd. Or you can just simply say it's 2 molecules, 13 molecules, 8 molecules, 10 molecules. But 1 mole of easy substance is 6.02 times 10 to the 23rd molecules of that substance. So I teach this in 2 ways. I say, okay, that's 2 molecules, or 2 N sub O, where N sub O is 6.02 times 10 to the 23rd molecules of whatever you're working with. Here, this is 13 times Avogadro's number, 8 times Avogadro's number, and 10 times Avogadro's number. So you've got the real numbers of molecules running around in your reaction chamber, if that's the equation you're working with. Another item that you can calculate from equation are gas volumes. Now, gas volumes are expressed in what we call molar volumes, V sub m, where Vm is, and you can see it in your handout, a molar volume, and you'll see it down there at the bottom. You look in the handout. 1 molar volume is a volume occupied by 1 mole of any gas. It doesn't matter. CO2, S2, H2, whatever. It is 1 molar volume. Now the problem with that is a molar volume can change because of temperature and pressure conditions. So in order to have a specific standard volume, we call molar volume, we have to also establish specific temperature pressure conditions. And with the standard equation, now what were the conditions that I told you earlier? 0 degrees Celsius and 1 atmosphere. Now, with that, you can define a specific volume occupied by any gas, and it turns out to be 22.4 if it's at 0 and 1 atmosphere. Another standard is called thermodynamic standard, which is 25 degrees, so it'll be a bigger number, 24.45 liters, and we'll use that later on. So, if it's a standard, you understand this is already at 0 degrees Celsius and 1 atmosphere. So you could say, okay, this is 2, that's 2 molar volumes, regardless of the conditions. You don't know, if you're not specifying the temperature pressure, you don't know what the volume is. You can't. But if it's standard, then you stick 22.4 in VM. Here's 13 molar volumes, 8 molar volumes, and 10 molar volumes. Now this will be 2 times 22.4 liters if at 0 degrees C and 1 atmosphere. This will be 13 times 22.4 liters if at the same conditions, 8 times 22.4 liters, or 10 times 22.4 liters if at 0 and 1, 0 Celsius and 1. You change that temperature and you do not have 22.4 again. Energy numbers are proportional all chemical reactions. Doesn't matter. Reactants go to products plus energy change. Doesn't matter. Now there are 2 kinds of energy changes. A change in which the system, the entire reaction loses energy, or the entire reaction gains energy. But whatever it is in the context of this, it's reactants goes to products plus an energy number. that energy number is proportional to the coefficients of the limiting reagent. What's a limiting reagent?